Some of you might be already familiar with how CENOS simulation tools look like, and liquid metal steering from the workflow perspective is not very different from the others. What you see in front of you is the desk view of CENOS. You can see that the desk view is already divided into 4 parts, so 4 specific sections that represent also the workflow of the simulation setup. So we start from the left with the geometry definition, either by generating automatic templates, uploading your own CAD files, or building your CAD files within CENOS. Then defining physics on top of them, so material properties, operational parameters, and so on. Then you can mesh it, either let CENOS automatic mesh do the job or make manual modifications, and in the end, take a look at the results once the simulation is done. Today, specifically, we are going to take a look at the from CAD approach, as this is the most widely used one approach where you can simply upload your own previously created CAD file and use that as a base of your simulation. So as I said, today we will be building Induction Crucible liquid metal mixing setup, and I will start by importing the geometry. So the supported CAD files are step file or STEP, which you can get out from almost any CAD designed software. So we start by selecting the from CAD approach, and we need to select the CAD files we want to upload. So I'm going to click on the folder icon, navigate to the folder where I have my CAD file prepared, and upload it. So you can notice that at this point, I am uploading one specific CAD file. You can also upload multiple CAD files or put different parts of your system into different CAD files and upload them all together. That is also supported, and virtually there is no difference between the 2 approaches. Now, once I have uploaded my CAD file, CENOS asks firstly if I want to create automatic air domain. So CENOS does take care of some of the geometry setup, some of the geometry preparation, and yes, automatic air domain generation is the first step into this direction. Basically, when I click yes, CENOS will generate a domain or basically a volume that represents ambient environment where the electromagnetic field will be calculated. So you don't need to do that manually. You can let CENOS make it. Afterwards, we need to also specify the application which we are building at the moment. This and some other next steps, as you will see, are designed to simplify the workflow along the way. So basically, right now, by specifying either we have rotated permanent magnets within our system, or we have some coils as the source of our if we have some coils in our system, then CENOS will take this information and predefine and simplify a lot of stuff along the way, adjust the meshing parameters, adjust the resulting result visualization, and so on. So in our case, we have liquid metal mixing using coils, so I'm going to select this one. Now, at this point, we have come to what we call geometry roles. So at this point, we do not yet specify physical parameters. So we don't specify things like material properties or operational parameters. But what we do specify here is the content of our system. Basically, we need to tell to CENOS which parts are which of our solids are coils, which are the melt, which are the crucible, if we have included that in our system, and so on and so on. In the example I have uploaded, we have a relatively simple induction crucible steering system. So we have the crucible with the melt inside, filled up until the top, with a very simple 3-winding coil. So we simply start defining geometry parts. So I will start by selecting the furnace volume. by simply double-clicking and assigning it. I have specified that this in the middle is our furnace. In the same way, I will add also a crucible, like this. I will add 3 coils. So 1 coil is already given in the list. The other 2 I will add manually, like this. And now I also want to define the respective surfaces for our system. So what I want to specify is I want to specify the outer surface of the crucible, the top of the melt, and also the interface between the crucible and the melt. So I will start by defining the walls of the furnace. Yes. And I will select the interface walls. Then I will add another definition for the top and also specify the surfaces for the crucible. So as you can see, you can select either manually any face you want, or you can filter the face selection based on the geometry the face is a part of. So in this case, I will filter it as a crucible, and like this, I can simply select my outer geometries. This filtering helps if you have a bit more complicated geometries. Then you don't need to manually select all faces, but you can simply select the ones that are, but you can simply select them and group them all together. Now, in my example, I have defined everything I need. If you have different systems, and depending on what you have else in your system, you might have, well, you probably will have different role assignments. So depending on your system, you could have, for example, inlet-outlet surface definitions. You could also add, for example, ferromagnetic cores as well. Additional permanent magnets, and so on. Once we have defined the geometry role section, we can go further and take a look at the physics. At this point, we actually need to define all the physical input values that are required that are required to model our system. As you can see, physics part is split into different tabs. So you can see that each part actually has its own tab, which you can navigate and define things one by one, so that you can focus on one specific definition at a time. We always start the definition at the simulation control. So these are the general system parameters. And here we define, you could say, simulation-wide parameters. So we need to specify, in this case, things like operational frequency for the coils. So we could have it, for example, at 100 Hertz. We could have it at 1 Hertz. We could go even higher. We don't really have any limitations on this. And the other input that we definitely need to have here is the end time or the process time. So basically, for how long we want to model our system working. So I will put something like 30 seconds, for example. In between these two inputs, you can see that you have also control over the type of analysis for hydrodynamics, thermal, and electromagnetics. Now, for other tools, other simulation programs, multi-physics simulations can sometimes be quite hard to set up because you need to couple different modules to actually cover multi-physical phenomena. CENOS has automatically coupled hydrodynamics with thermal with electromagnetic analysis, and the only thing you need, or the only thing that you if you want to, you can change, is the analysis types of these. So for hydrodynamics and thermal analysis, you can choose between transient or steady state calculation, and electromagnetics support either time averaged or transient calculations. And that is it. For time steps as well, you can choose either adaptive time stepping or specify your own constant time step. Adaptive is definitely good enough, at least for first initial estimation, so we can leave it as is. Now we can go through and specify the physical parameters for each of our system parts. So we can start with the furnace. So the furnace, or the melt, actually, is like the goal of the simulation, where the liquid metal mixing actually happens. And for this, we do need to specify a couple of things to make the simulation work. So the first one is the material. You can select many different types of already predefined materials in our material library. For example, for this case, I can choose aluminum. And for this material, you can already see all thermal, fluid dynamics, and electromagnetic properties predefined. So you don't need to worry about any of these. You can simply click apply, and your material will be assigned. If you want, all our materials are completely customizable, so you can either change existing material properties, or you can simply create a completely new material, save it in your own custom material library, and use it in your future projects. On top of the material, we also need to define some additional things for the melt model to be defined from hydrodynamic perspective, from thermodynamic perspective. So what we need to specify is the gravitational direction. So in this case, the system is positioned so that the gravity is pulling downwards. So I will simply select gravitational direction as -z. Then we can also change turbulence models if you want to. So by default, we use K omega SST, which we have found to be working quite nicely in most of the cases, but you have some additional options present as well if you need. As for the boundary conditions, we have split the surface of the melt into two parts. So for both, by default, CENOS has assigned solid wall. On the top, we could actually change it to free surface. So basically, what these definitions mean is either slip or no slip condition to to take into account if the fluid is in contact with a solid surface or with a free surface such as air. If we scroll down, then we also need to specify the initial temperature of the melt. So we can do it either by defining a constant temperature, let's say 700 degrees over the whole melt, or we can initialize with a temperature gradient, meaning that I can, let's say, specify the lower temperature to be 700 degrees, the upper temperature be 800 degrees, and to give my temperature distribution a direction, I can give it, let's say, +z, meaning that with this definition, now on the bottom, we are going to have 700 degrees. On top, we will have 800 degrees, and we can, and CENOS will assume a linear, gradual distribution of this temperature. Basically, yes, you also have some controls over the boundary conditions for thermal analysis. So by default, we assume here to be thermal insulation, but you can also define a fixed temperature or some kind of a heat flux. For the interface between the crucible and the melt, I'm actually going to change it to interface to make sure that the heat transfer also is taken into account between these two bodies. And for the furnace definition, that is it. Now, as a next step, we can go into the crucible definition. And basically, we have a very similar definition as we saw before in the furnace, except without all of the hydrodynamic inputs that we needed to define for our melt. So for the crucible, copper is already assigned as a material, but of course you can change it if you need. So honestly, the only thing we need to define right now is the crucible temperature, which I'm going to set to 800 degrees. Now from physics, all that is left is coils to be defined. So I can simply go into the first coil, for example, first winding, and here you see that material as copper is already predefined. So I'm going to input a current, so let's say 10 kiloamps. I can specify a number of turns, and for mixing systems with with the moving magnetic field, you can also specify a phase shift between coils to create a traveling electromagnetic field. In this case, I'm not going to do that because for the induction crucibles, usually this is not used. So I will simply define 10 kiloamps of current for all 3 of my windings, like this. And honestly, from simulation perspective, we have set up the case completely, and the case is actually ready for calculation. Now, I know what you might be thinking, we did not mesh it yet, and that is correct. CENOS does include quite nice automatic meshing algorithms, meaning that we could technically run the case directly right now. CENOS would mesh it on its own and provide the results as CENOS sees fit. However, of course, we can also take a look at the meshing section by simply going and navigating into the meshing part. So before calculation, what we can do is generate the mesh. Now, what CENOS will do at this point is to generate the mesh as CENOS sees fit, and we can evaluate the mesh and modify it if necessary. So let's give it a couple of seconds. All right, here we have it. So CENOS has generated a mesh. You can see that for the crucible and for the melt, mesh is a bit more finer than for the coils. Honestly, for the coils, in this case, I would even go with a bit of a finer mesh. So how can we actually change the meshing parameters is we can enable mesh refinement. And through this, we have full control over each of the solids here within the mesh. And we can, for example, go into the first coil, change the element size for the whole volume, and we can also play with what we call skin layers. So basically, for deeper evaluation, you can enable mesh cutting. And with this, you can actually take a look at what's inside of the mesh. And if we do this, then you can notice 2 things. So first of all, CENOS automatically generates what ANSYS calls inflation layers in the coils. And it also generates viscous layers in the melt, like this. So all of this is done automatically, but you have still full control over the mesh and also these layer parameters. So if we want, we can go, for example, into the first coil. We can either change the total element size, or I can even select a specific surface or edge and refine the mesh on this specific part of the system. So yeah, if you are not confident or you want to refine your system mesh even further, you have full capabilities of doing that. At this point, we could, run the simulation, which I'm not going to do at the moment, simply to save some time. But I have already calculated the results of this case. Once the simulation is done, results will pop up in a separate window in one of our third-party tools, PataView, with already some pre-made customization. During calculation, you will also get some information about the progress, things like minimum maximum temperatures, so you can actually follow the mixing process as it is being calculated. But in the end, of course, you will also get a lot of visual data out of it. Once the simulation is done, results will look something like this. So to those who are not familiar with ParaView, this is a very strong post-processing tool, which allows you to do a lot of different result modifications. What we have done is we have already prepared the results in some way. So similarly, as we had tab-like navigation in the physics, in results, you can also on the top here see we have separately shown thermal analysis, flow analysis, electromagnetic analysis, and also what we call time charts, which basically gives you information about the heating power, that goes into, in this case, crucible and furnace itself, and also temperature dynamics. So this, in my perspective, is very useful because in this graph here, you can follow minimum, maximum, and average temperatures within your melt, and by doing so, see how the mixing actually progresses and if the mixing actually happens, or and yeah, not only if it happens, but how quickly it happens. So here we can very nicely see that we in physics defined minimum temperature of 700 degrees, maximum 800 degrees, and we can see how these two minimum and maximum values are actually converging. Now, if we look at the visual result analysis, you have full capabilities of visualizing fluid dynamic or thermal results in a lot of different ways. So, for example, for such result visualization, what we could do is we could, of course, slice it so that we can take a look inside. So by doing so, we can visualize the mixing dynamics inside the melt. Of course, from this kind of a visual surface representation, it is quite hard to understand actually the fluid motion. So what we can do instead is show it with vectors like this. So we can very nicely see how the coil positioning, as we had 3 coils centered in the middle of the melt, how they actually create these 4 separate turbulent zones. And we can see where the flow velocity is the highest and where it is lowest. And from this, we can actually visualize on this same cross section, we can visualize not only velocity, for example, but temperature as well. And we can see and also follow the thermal field, and we can see how it actually very nicely interacts with velocity distribution in the melt. We can, of course, also evaluate the dynamics itself. So we can go to the beginning of the simulation. We can rescale the data to 700 and 800 degrees respectively. Oh, no, not that one, sorry, this one. Yeah, just to represent the initial conditions better, you remember that we defined the thermal distribution with the gradient, so we can see that the bottom is coldest and the upper part of the melt is hottest. And we can see initial gradient, and if we go next to the 30-second calculation, with this scale, it seems that it's completely uniform, which of course it is not, and we can rescale to the end data to see that there is actually a couple degree difference still within the melt. And yeah, from the setup demonstration, I think I have covered everything that I wanted to. So today we focused on induction crucible setting up and simulation, but that of course is not the only application CENOS liquid metal steering tool is capable of simulating. We can also simulate different kind of continuous casting, continuous mixing processes using different coils or also rotating permanent magnets. Before we go into the Q&A session, Q&A part, I also wanted to sketch out what we are planning to do next. And honestly, today's presentation was a slight snapshot of our next release, which we are preparing and are expecting to release in a couple of weeks, where we are going to actually add the possibility to include crucible in the thermal analysis, as well as ferromagnetic core with full BH definition to take into account also saturation effects. Besides that, in our future roadmap, and here I want to outline that this is in no specific order because the feedback from our customers is, at least initially, the biggest driving force for the CENOS simulation tool development. We are planning to include coil grouping for induction crucible easier setup, solidification modeling, 2D electromagnetic modeling as well for increased calculation speed in axially symmetrical cases, include improved post-processing and also runtime post-processing. So basically what we want to do is move all the result manipulations within CENOS to simplify them more than they are right now, and to give our users more data to work with. And yeah, I think at this point we can move forward into the Q&A session. So please, if anyone has any questions, I see that my colleague Didis has also joined, who is actually our product engineer for CENOS liquid metal steering. So together with him, I think we can answer any questions you guys have. So please go ahead. Yes, Andres. Hi. Long time no see. You're muted. Yeah.
Nice to see you. I would like to ask about this apparent simplification of the induction coil definition. So we could not see now the terminals, which were usual in induction heating, and somewhere the definition you had to define that one coil has one turn, so it means that it could have also multiple turns. Please tell something about this philosophy.
Yes, this is currently a way how we approach solenoid coil modeling. So we don't extrude the terminals, but we model each of the windings as closed ones. So for this purpose, we need currently to define each winding in a separate tab and define the electric current on it directly. Number of turns is more for the potential application of stranded coils, not as much as the number of windings actually in a solenoid coil. What I mentioned for future development is the possibility to group actually these coils, because specifically if we talk about a induction crucible melting and mixing, then the coils could have potentially a lot more windings, and it could be tiresome to define each of them separately in any case. So that's one of the things that we are still looking to improve. But yeah, Didzi, maybe you have some comments here as well.
I see. Thank you.
Yeah, it's like you said, right now, current and number of turns is simply like different ways how to define current for these coils, but in our future releases, we have plans for improving these definitions and adding some extra features. So yeah, but of course this is also dependent on our customers and their needs. So we'll move appropriately.
All right. If anyone has any additional questions, please feel free to either write them in the chat or speak up. Either way, if even after the meeting, sorry, the webinar, you found yourselves wondering about some specific things, or you remember some specific questions, or you simply have an overall interest into liquid metal steering app being tailored or adequate for your simulations or your systems, then please feel free to reach out to us directly, either via CENOS webpage, or I think you could also, yeah, I think via CENOS webpage would be the best way to go. Okay, if no additional questions are present, yeah, Maddie, thanks. Thank you for thank you for the comments. I really hope you guys enjoyed the presentation. As I said, it will be available on our YouTube channel. Thank you for joining. We'll keep you updated about the next steps and next progress, and potentially let's see you all into the next webinar about liquid metal stirring. Have a nice evening and have a nice day to those who are joining us in the morning, and see you all next time.